Yeah. All right. So where did we stop? Sorry, I'm just trying to share my screen. Well, we're talking about why the MAE is so large. The thing is, both the MAE is not incapable as a value of being large. It can actually be extremely large. What the MAE, the mean absolute error, does is that it measures the accuracy of the model. That is how well the model is generalizing to new data points. And that's all. It doesn't necessarily mean that the all right. As I was saying, what the MAE just does is that it captures how well the model is performing. The higher the MAE, the more poorly the model is performing. And the lower it is, the better it is performing. You can have an MAE as low as something of 0.222 like that. And you can have an MAE as high as something of 2000. It's just that the higher the value of the MAE, the more you have to do to improve the model. It just means that that current model is not the line that the model used to fit the data is not proper enough. For instance, our current model will be operating at something, say, let the line be somewhere here. So that's the reason why we're having that MAE that high, the MAE value that high. And this can be, with this now, we can say, okay, let's adjust some of the values, the data here, to make it more convenient for the model to predict the value. It's just from the values generated from the MAE that we know what to do to improve the model. So
I want to ask a question.
I'm listening.
Could it be that it's because the values of those targets, they are very large? That's why the MA is this large, like 854 or something?
No. That cannot be the reason. The values from our variables, they don't actually determine, like what the values try to do is, they try to make the predictions on the target system, meaning no matter how high they are, no matter how low they are, the volume, or what's the word, the higher the value is, right? It's just that the more time it will take for the model to process it. That is just it. But it doesn't really affect the overall aim of the model, which is to make use of the values now to predict what the target result should be. And yeah, we can visualize the model. The thing is, I didn't really, if you wanted to visualize a model now, I got a question now. If we can visualize our model using a scatter plot to see how the model is. The truth is, we actually can. But if you wanted to visualize the model, you can't visualize it on, say, all of these columns now. You could do something like, let me make use of a C-bomb to visualize the relationship between the one of the continuous variable that we know of, which is the item width. I think is one of the continuous variables that we know. So I say Sm is rel. Oh no, I have to make it of a rel plot, which is a regression plot. So regression plot. So the x should be the item and the square width x, and the target should be the item outlets sales, the item outlet sale, where the data would be the big mark now, because it's the one that actually contains both the item weight and this thing. So making use of this, so HMS is not defined. I'm putting in particular so what sleep on. So this is a really huge distance because it has about 8,500 this one. Maybe that's just different time. So that's it. Now this is the relationship between the item weight and the item outlet. You can see that there's almost no linear relationship between them now. So you can see why the model is struggling. And this is just with a single variable, just one variable, which is the item weight, comparing the item weight with the item distance. Now, in this model, we have categorical variables that is making use of. We have VA variables, that's values like 1998, 1990, and we are trying to say, okay, make prediction, then combining all of these variables. Now, the more the future columns in the listing, the harder it will be for the model to actually learn. Not because actually it's supposed to be easier now, it's supposed to be easier, or it's supposed to make the model learn faster because there are a lot of the more future columns exist, um, the more reasons you can find why the value are appearing the way they are. You understand? If we were to make use of, say, this particular value, maybe we'll be fitting a line. Just if we were to create a model between the item weights and just this, we'll have a high accuracy because it will just draw a single line here, which is what is predicting. But now, the linear regression is doing more than just that. It's working with as much as this. So visualizing this particular listing, this data points might be difficult to work with. This is just what we did here. Just what do I call it? We just like did a dummy test on the linear regression. We should proceed to looking at other ways that we can check the model performance. One of the most useful ways is to make use of the cross-validation score. What I like to do is I like to list out the models that I feel would address this problem. Where one of the models that I know actually would address the model because I've actually tested it in our notebook. And what we realized from the end of our analysis is that the model that performed best on this remote our tax. Okay, the the linear regression model, after performing cross validation on it, the mean value had was 912, which is kind of even worse than what we did here. And the reason why it's worse is because when we trained here, we made use of and we splitted the data just into two sets, having 6,818 sets for training, 1,710 sets for testing. That is, it had enough data to test. But what I did here is I performed a process called cross-validation. And what cross-validation is really all about is when we have our data sets, what we have here, we have the data for training, but we don't want to just test right away like what we did here, where we trained the model and the training this time. Immediately after training the model, we just tested it. We checked how well the model can generalize. But what we really want to do is want to always, after training the model, to validate it to see, okay, is this model actually performing well? If it's not, then we train it again, validate it, see performing well. No, we train it again, like that. We keep switching between these two till we get a model that actually performs well with as little data as possible, but on new instances. Then after this model performs well with just the training, this has not seen the test data before, then we can now predict on the new data. What the process of doing this is really simple. It's just what we did here at this point. I copied the whole of this value here. That is the X twin, X test, Y twin, Y test. And I just paste it here. So instead of tests, I will change this to tests. This to tests. And this to text to the value val. Now the val stands for validation. So instead of making use of the data and targets now, which is our overall data and our overall target value, I'll make use of the X twin and X minus X twin and the Y twin. I'll make use of the X twin and the Y twin. Now that is, I'm getting the exact, I'm getting the training data. Now that is, we've dropped the test data to be on its own. We're not making use of the test data anymore. We want to make use of only the training data and the testing data to create a new set of training data and a new set of testing data, what we call the validation data. And the validation data is what we'll now make use of to test our model to see if the model is actually performing well. You guys will still understand what I'm talking about. So this is just it, and I'll say I want to check the values of this. So now our training data has been reduced to about 5,454, and the validation data is now 1,264. Okay, so I'm having a question here. Why are we capitalizing X and not Y? Well, it's just a convention, honestly. If you realize, if I open this documentation, what we have here is when they wanted to input the first training and test in what we see here, what they call here is X and what they call here is Y. The reason why they do this is from the math formula itself for performing for linear functions, the mathematical formula. The X character is always capitalized, while the Y character is always, left in its lower form to indicate that it is the target, Y is the future. Not that X is not representative or enough of it, but it's just a convention. It doesn't really matter. It's just a convention. So now that we've been able to get our the training and the evaluation, what I like to do is we'll be making use of a new model now because we've made use of the regression model. I just wanted you guys to see how it works. The linear regression model is like the oldest form of actually finding a pattern between the points, the data points. I think it will be easier to visualize. Okay, yeah, so this is the line. This is actually how the model is performing this case. I just wanted to do that to see the line. So as I was saying, okay, now that we've had the training and the testing and the validation sets now, this tree set is what we actually make use of to check how the model is performing over time. So we'll be making use of the training set now to work on the random forest model. So I'll take from and the random forest regression is actually an ensemble model. What that means is that it's a model of models, and the other models now is the decision tree regression. Basically, ensemble models are like a collection of different models that are working together to make a picture. The random forest is a collection of decision tree models, and the number of decision tree models that are used is actually depicted with the variable name. The variable name n estimators. That's the random forest regression. The n estimator here, this value, it says that how many decision tree regression we want to make use of. The default is always 100, And that's just the default parameter. And if you realize, compared to the linear regression model that has just few distinct parameters like intercept, normalize, which are not really important and doesn't need to be changed. The random forest has a lot of parameters that can be tuned to improve the model. So if you make use of the random forest regressor, the first value you get is not necessarily going to be the best value. But by the time you start adjusting these values, changing values like the criterion, the max depth, the mean sample split, and all of these values, you start getting different results. So you start, this is the process of fine-tuning the model. You start asking the model to adjust its parameter to suit the need of what it's trying to predict now. So that went to, I'll just call for I'll just name the random forest regressor, random forest regressor, model. So one thing I like to do is I like to make use of the cross-validate score to check just how well the model is. So from model selection. We try for cross-validation score. Says, okay, let's see how this model will score if it's being cross-validated. I just say I'll actually say it in variable called scores. I'm trying to get the scores of this model. Maybe if I even say it, but let me just show you guys what we have. So the cross-validation score takes the model that I want to make use of now to analyze the result, the performance. That's the RFR model. It takes the data, which is going to be the X string. It takes the target, which is going to be the Y string. And then it takes other values like the CV, which is saying the cross validation. It asks how many distinct folds do we want to cross validate it to. And you can know more about cross validation by reading on the k-fold cross validation, just to give you an intuition of how cross validation actually works. Then one other essential parameter is scoring. The scoring is like, how do we want to score the model? That is the model performance. We want to know how well the model is performing, just like as we made use of the metrics here, the mean absolute error. Now, it's not just going to be called the mean absolute error when you could just come here and say something like mean absolute error. If you run it now, you have an issue. It says key error. It says the mean absolute error is not valid, is not a valid scoring value. So it asks you to check for. You could actually check the reason why this is not the simple. The mean absolute error is not a valid scoring value, whereas we made use of it here. What's its the name the scikit-learn or the official documentation used whenever you want to apply the mean absolute error in checking how the model performance during cross validations to add this little addition, the NEG for negative mean absolute error, and it just returns the negative score of all of them. You notice it will take a bit longer. We should have reduced the size of the data set so that we have to.
I have a question.
Okay, I'm listening.
This cross validation that we use, is it k-fold or stratified?
The cross validation
Is it K-fold or stratified or
Is
leave one? At which one?
is K-fold by default. It's K-fold.
Okay, K-fold. Okay.
By
What about
default.
this NEG? What does it mean? Neg.
The neg is it stands for the negative mean absolute error. That's the reason why we have a negative sign in all of the cross validation score.
Okay.
One way you could remove the negative sign is to just add a negative value in front of this. Since the what is being outputted now is an array, and you know that once you add the negative sign, it does the it does the computation automatically for all of the values. Yes, so negative become positive for all of this. So just store this in the variable equals this. I'll just come here and I'll ask for the scores dot mean. Then I'll first ask for the scores then. Scores dot mean. So so this the reason why we have positive values now is because of this negative value that I added here. Because when we perform the cross validation with this scoring, what it did is that it found the negative mean absolute error of the performance. So giving it a negative sign in all of this point. So by adding a negative sign here, I was able to convert it to a positive mean absolute error. So that is just a quick listing for converting it. And these are the prediction the scoring for each field. That is 780%, 780 score for the first field, 822 for the second, 773 for the third, and then you had an average of 800, which is slightly better than the linear regression model. And this is without actually fine-tuning the model to see how it works. Now, what I created this particular function here is something like a how do I put it? It's a general function that takes as much model as possible. It takes as much model as possible, and it performs cross validation on all of those models, making use of the training and the validation sets. And quite all right, I won't be making use of this function this now. I want
Excuse me, I have a question.
Explore the function itself, and I gave a task at the end. You can try to recreate this function to the form of a class. That is in form of a class. I really love to.
Sorry, excuse me, I have a question.
Function. But when you are performing a model, you will realize something. When you are performing,
somebody has a question.
When you are checking for a model performance,
it's not hearing us.
one of the things you realize is that you copy this specific process that we did here for the linear regression, the fitting and the prediction and the mean absolute error and the scoring and all of this stuff. You see that you often read over and over and over again. So in order to avoid this loop or this thing, you just need to create a function that will do one thing for all of the models. Say the linear regression model, the random forest model, if you're making use of the k-nearest neighbor regression model now, you can make use of that too. So you just create a function that does all of this. And I'm just giving you guys like a hint of how to speed up the process of evaluation, because it's a lengthy process. It's the only process length that is more length, second in terms of length, in terms of time consumption when you're actually working on machine learning projects, other than data cleaning. Data cleaning is a very, very lengthy process actually. What we did was just something brief because we wanted to move and get to this stage as soon as possible. But when you are performing model selection, the lengthy and the time-consuming process is actually the training period and the period where you check the accuracy and all of this stuff. So you can just create a function that will do all of it at once. Once it does that, you can now be viewing the model performance, kind of what we did here now. All of this was just like I was trying to show you guys how things were working behind the scene. So if you realize we did something for the linear regression model, we performed cross-validation on it, we checked for the mean cross-validation score, and we performed grid search on the specific model now. So the grid search is another, what's the like for it? It's another way of evaluating a model. But the beautiful thing about research is it gives you the ability to actually change the parameters of the model. So the grid search is also a model selection process. So you just make it of the scikit-learn dot model and what's called selection. Okay, someone raised their hand. You want to ask a question? I'm listening.
Okay, thank you. Yeah, I'm of the opinion that if you are using different algorithms, are we using the same text and train data sets? And if possible, if you can just take that process, because that's where I'm really getting confused when it comes to aspect of choosing different algorithm, different model. So we can just please explain that very well so that we can understand. Thank you.
Okay, I didn't really get the question. Your voice was breaking. You said the train test process. Are you talking about this particular process here?
Yes, I'm talking about no, I mean the model. Yes, I understand it up to where you have to split it. Then okay. I don't know why you have to get validation data again after the test data.
Okay.
I don't know why we need that.
Okay, let me quickly explain that. The validation data is not always necessary. It's just that it's recommended. Now, when you make use of the training data, and when you make use of just this train and test data, what happens is that immediately you train on this whole set, and you test it immediately on the testing set, which is this set. And that is actually good enough, because the reason is that the model is not actually seeing the new data. That is this test data. Since it wasn't used to train the model had no idea what the value of this data should be. So it would work. But the reason why we make use of the validation data, which is what we did here, when we created the training data and the validation data helps us to keep this testing data aside. Like we won't make, like it would be like a session of data. Okay, let's put it this way. It will be like we are trying to give the students a practical exam, like the model, a practical exam rather, and then the practical exam will be the validation data. So when we train it on this model, we train the model with the trained data, we give it a practical testing with the validation data. After seeing how the model performs on this validation data over time for various models now, which can be for both support vector model, the support vector machine model, the random forest regression model, we tried this for various models. The various models have just been making their prediction on the validation data alone. Now the test data is still separated. The models have never seen the test data at any point, and the validation data has the integrity of always being new whenever we are validating the results of the model. So when we've after evaluating on as much model as possible, and we've come up with the optimal results now, the optimal model that we feel will best suit the task, we now make use of the test model to now see how well it generalizes. That is after the whole process of doing the training and the training and evaluation and training and evaluation. The validation data acts as a evaluation testing process. It just helps us to give the model a form of practical testing. Then when the model, we realize that, okay, there's this candidate model now that performs best overall. from the series of models that have been doing the practical exam, and I say, okay, since this model performed best, let it now take the main exam, which is going to be the test data sets.
Yeah, thank you. I understand now.
All right.
So can you please now explain the process of choosing the different models, the different algorithms?
So the process to choosing the different model is actually, as I said, is a lengthy something. It's a process of where you first start by shortlisting the models that you feel should work properly for the task. And that's what I did here when I elected all of this model. That is the XGBoost regressor, the support vector regressor, the decision tree regressor, the k-nearest neighbor regressor, the linear regression, and when we've elected all of these models, now these are the candidate models that any of them can actually suit the tasks that we want to work on, but we want to see which one will actually perform best. So we split the data into three. The first is for training, the second one is for validation, that is the practice exam. Then the third is for generalization, that is the final exam. So we now perform a loop now. As I said, this function is actually complex. And the goal of the function is that it performs both cross-validation and grid search analysis on the models, making use of only the training data, making use of only the training data and the validation data. The test data is not even going to be seen by any of the model at any point here. So after it has gotten, it has trained on these models, we now go ahead to check our values, and these are just the parameters that were passed. I think this for the linear regression, this for the random forest. I think this should be for the decision tree, this for the support vector mesh, not sure. This for the regression. This for the k-nearest neighbor. These parameters, that's when performing the grid search now. This particular variables here is for the random forest. And the last one is for the XGBoost. So it performs the analysis on all of them. Then at the ending, we have a record, something that is like this, that states the validation score of each of them, the cross-validation mean, the value from the grid search. And we looked at how the grid search estimator now, which is the best estimator when it mixed all the values together to see the results obtained. What is the final prediction from the grid search? And we kind of get the MAE of it and compare the MAE from the grid search with the MAE from the cross-validation process. We do the same for the k-nearest neighbor. These are the results. We see that the k-nearest neighbor actually performed worse than the linear regression. We do the same for the decision tree. We get the results. Now, this is the result for the decision tree. The same thing for the support vector regressor. We do the same thing for the random forest and like that. Then we kind of compare their performance. At a point, the random forest regressor actually had a score of 664, which is the lowest from this thing. Okay. I have a query. I got a question here that what does the grid search does? Okay, the grid search, what the grid search does is that given, say, this, we have a model now, this model, the random forest regressor. What it does is we create different random forest regressors. Think of it as creating different random forest regressors. You can create as much as 100 to 10,000 random forest regressors. The thing is that for each regressors, they will have different values. Like here, the criterion, instead of being the MSE, which stands for the mean square error, could be the MAE, which stands for the mean absolute error. And the depth will change, the mean square, mean sample split will change, and all of these values will be changing. at each point. So it creates different models with different parameters and fits all of this model with the training data and perform cross-validation on that data. And it looks for the model with the best, which has the best parameters, which performed best rather. They look for the model which performed best among all of those 100 to 10,000 models, and it's presents it in the variable here called the best estimator variable. Now, this best estimator variable is now the best model from all of the models that was used to perform the grid search now. That was used when you perform the grid search. It takes the best model and then it says, let's try and see how the model performs when we fit it with the training data and evaluate it with the validation data. And this is what we get from this is actually the error from the grid search. When we use the random forest, it got 775, that is 775 775 MAE for the grid search and 784 for just performing a common cross validation. So that is for the first question. The second question is, how do we go about functional pipeline that automates the process? Yeah, that's an interesting question, and it's one of the points we're actually heading to. And we'll get there when we start with the classification task. I intentionally didn't do anything about it in this video because I left a task for those that might be interested to see how they can do it on their own first. But I will actually take the process of showing you guys how to create a general pipeline that does the process from the cleaning to the prediction. But it is very good that everyone understands what is actually going on behind the scene. Because if you don't get this process now, the pipeline wouldn't make any sense to you at the end. So that's just the reason why I'm trying to be as explicit as possible. And I always try to do more talking than this. And we made this book to just give everyone an overview of what we are trying to actually do. One thing you can realize is from the random forest regression, the model that actually performed best now, that is from the test result that we actually did in our notebook here. The mean sample split, the best value that it felt the model should have is 10, and the number of estimator it felt the model should have is 300. Now, if we were to create a new model in our practical, having this particular estimator, the value we got here should improve. Compared to what we really have here. So I'll just quickly do that so we can see if what the grid search analysis did for us is actually true. So I'll just say Ctrl C, copy those values.
Hello, excuse me. I want to say something.
I'm listening.
Yeah, you wanted to do something with this with this grid search that you were, yes. Can you just do it, the practical of the grid search? Let's see how it works, the practical of it.
Yeah, I'll do that now.
Okay, thank you.
So instead of waiting for this stuff to be downloading, let's just say, okay, for the grid search now, I want to tune the parameters. Okay, we got the MA of 788, which means it actually performed better this time around. But okay, for the grid search, the way we create a grid search is saying that's the I like starting with the cloud system first. So the grid search series. And okay, this is what will happen. I will end this video here because the time is already up. So in the next video, I'll just explain the grid search and I'll call it a night for now. So everyone is just clear on what's the grid search CV, how the grid search CV actually works.